we had come up to this point right here. So that's basically why I did those little side reactions. But I guess I should talk a little bit about this epoxide here. So this is a common building block because it does have, as in Joel's question, it does have two electrophilic carbons, here and here. So after the first reaction, if you have some heteroatom, and we'll just call it X, and let's call it R. So this could be nitrogen, could be oxygen, it could be sulfur. If you're doing another reaction on an epoxide, remember if it's under basic conditions, and we did this in class, in the Organic 2 class today, under basic conditions, the nucleophile will attack the least substituted carbon. And if you could do the reaction under acidic conditions where you protonate it, so the nucleophile would attack the more substituted carbon. So there was two ways to do it. In each case, it would always be attacking through like the opposite side, so opposite side. So there would be some, the nucleophile would be anti to the oxygen. But so under acidic conditions, the more substituted carbon would get attacked. Under basic conditions, the least substituted carbon would get attacked. Typically, more often than not, the reactions that are taking place are basic, under basic conditions. Under acidic conditions, typically the nucleophile under those cases would just be water. So you're making a diol. That would be the main one. I think that's basically where we left off. We were talking about using two functional groups in one step. So the next thing that we were interested in was, if we do this sort of systematically, is that if you've got a heteroatom on the carbon next to a carbonyl, this is a common sort of reaction to use. You could, because this is a nucleophile, you want this carbon here to be electrophilic, so a positive charge, and so using a bromine, a chlorine, or an iodine we call these alpha halocarbonyls. These tend to be quite reactive. They're very good in SN2 reactions. So you can displace it. Here I'm using an imidazole to come in and attack, but this would basically because the conditions that are favorable for an SN2 reaction would be favorable for here, because it is an SN2 reaction. So things like aprotic solvents, if this carbon didn't have too many substituents, that's helpful because it works best on primary. Technically, it could work on a secondary, but a secondary one, but slower. So those sort of considerations. There is, yeah. So those are that's the main. So that's a common sort of reactive electrophile. For if you've got a carbonyl and then there's a heteroatom right next door. Nitrogen, oxygen, sulfur, those ones. Now, the next part is if you've got two heteroatoms on the same carbon, and most of these are basically certain functional groups that, like, if you've got carbon, oxygen, carbon, oxygen, carbon. These are acetals. That's just, we did that in Organic 2. If you've got the same thing, but with sulfur atoms, this is a thioacetal. And it's very similar. all of these sort of structures can come from, in this case, aldehydes. So using excess alcohol, catalytic amount of proton, and you're going to disconnect here and here. Thioacetals are very similar, except for you would use a thiol. And some of the, instead of using an acid catalyst, typically they use a Lewis acid catalyst. But yeah, here's thioacetal, it's just basically right here. And if it's connected by carbons, this is just decreasing the, it's just making the, you're tethering your second nucleophile to the first, so it just makes the reaction faster. These other ones are slightly different. This one here is what we would call a hemiaminal, which is oxygen, nitrogen, and a catalyst. So, but they all basically come from the same thing, carbonyl compounds. So this is apparently green leaf lilac perfume, an acetal with the dimethyl acetal. Just use some methanol, a little bit of acid, plus the corresponding ketone, and you're going to have your perfume, and it's going to smell wonderful. And that will be that. But we basically did this in organic 2. Now, there is a really interesting famous synthesis that is a 1-1 disconnection here. But it involves, so this is nitrogen, like an amine, and a carboxylic acid. So this is technically an amino acid synthesis. And on the carbon in the middle, you've got an R group, which is very similar to all of the chiral amino acids. So this is a way of very famous synthesis. So functional group interconversion, and then we have to sort of remember that a carboxylic acid comes from a nitrile. If you use acid and water and heat, maybe we'll do the mechanism in a second here. And so what we have here is that you can mix your ammonia plus a source of cyanide. In this case, they're using HCN. The pKa of this is very low, so this is a relatively acidic proton. So amine plus carbonyl is going to give you NH2, and this is going to have a positive charge. You have some water, and actually I've already deprotonated the nitrile. Nitrile comes in, attacks, and you basically have your intermediate here. And then you would throw in some acid and heat it up, and boom, you've got your carboxylic acid. So here's the actual synthesis. So NH4, this is basically just the protonated form of NH3. KCN, now we've got a more basic nucleophile. You get your product, heat it up, and bang. That is the Strecker synthesis. And if my memory is correct, oh, I might be thinking of someone else. I think he was working at the University of Alberta when he discovered this. I have to look that up. I can't remember, but that makes Could be wrong. But anyway, if we here, bear with me for 1 second. So if you've got a nitrile in a acid solution, what's going to end up happening is you're going to end up protonating. It's going to get protonated, and then you've got a bunch of water. And so it'll come in, and this protonated nitrile is very similar to a protonated ketone. You will form oops, yeeks, that plus. Now this is all about like transferring protons around, and we've got this. So this would be in resonance. Let's draw a resonance structure just for the sake of it. With this. And in both of these resonance structures, there's something in common. We've got a positive charge beside a carbonyl. So this is going to make this carbonyl a little bit more electrophilic, so more water can come in. And this would all be in equilibrium, but the equilibrium is going to be shifted to the products in a second. So we'll have this. H2, proton transfer. So we'll do it as an intramolecular thing when we do it like that, just for the sake of it, speed things up. Now it's got a positive charge. And last but not least, either one of these oxygens can boot this guy out. And we would have RC OH NH3. And this would quickly get deprotonated. And we're going to have our carboxylic acid. So the neat thing about the nitrile group is that it can get converted into a carboxylic acid using a aqueous sort of acidic hydrolysis reaction. It requires some heat, but the other thing is it can get reduced into an amine by using like lithium aluminum hydride and some acid in the end. So or hydrogen with some catalyst. So it's a pretty versatile reagent in the sense that it can make an amine or it can make carboxylic acid. So that's kind of fun. Right, let's go back to where we started off. So the next section, this is most of the time like alpha halo ethers. These are, when we're looking at them, they are, so the carbon here is got, if you make the two disconnections here, we've got an alcohol and we've got a halogen of some type, so HCl. So the way that this typically works is that in the presence of HCl, your carbonyl is going to get protonated. And then you're going to form a hemiacetal, right? So alcohol plus ketone. If we're going on our journey to an acetal, the intermediate that we get to would be this. Would be this. And if it's in the presence of acid, this is going to get protonated and you're going to have a positive charge. And we can boot this out with our oxygen. And then from here, positive, the chloride would come in and you'd end up making your 1,3 dihalo. These aren't particularly stable compounds, but they are used quite regularly as protecting groups. And mem is just this is a protecting group for alcohols. We might see it a bit later on. This is the electrophilic carbon here. And so if you've got an alcohol with a little bit of base, like triethylamine or something like this, you would protect it as what we'd say mem OR. But the actual structure of this beast is so your main molecules here. And so the protecting group itself is carbon, oxygen, carbon, oxygen, carbon. So it's effectively an acetal. So we'll see going forward, particularly in one of the syntheses we do early on, that people have used these as protecting groups for alcohols. We'll see that in a little while. But this is basically this synthesis here, like formaldehyde plus hydrogen chloride gas, that's not how I would want to make it. No, you'd never want to. Using something which is a toxic gas isn't ever particularly fun. There's a neat synthesis of there's mom chloride, which is this methyl oxygen CH2 Cl. So it's very similar, except for it's methyl oxygen CH2 Cl. There's an interesting synthesis of this that was published, it was probably 20 years ago. So the Aldridge, which sells this stuff, mom chloride, the cost of it was pretty expensive, right? So one of the fellows at the University of Waterloo designed a synthesis using a different reagent that was pretty simple to make mom chloride, and it was wildly successful and it was cheap to make. And then what Aldridge did is it jacked the price of the reagent that was used to make it. It's kind of funny because they were losing business. But anyway, I digress. Okay, so now we're going to get to some of the stuff that we talked about in Organic 2 a lot. So if you've got a alcohol and you're surrounded by R groups, this is the very obvious disconnection that you can make. Because this can come from R minus and this carbon with a positive. So the common sort of reagents that are involved here are sort of Grignard reagents and carbonyls. And depending upon what you've got over here, R2 or R3, your carbonyl can be either a ketone, like in this case, or an aldehyde. And the fun thing about Grignard reagents is that they come from, X. Any alkyl halide, well, I shouldn't say any alkyl halide. They typically come from, so Rx, X equals Br, Cl, or iodine. And it's just, you just take those and you put in the mercury, sorry, I said that earlier today too, the magnesium. And then we all did this in the lab in organic too, right? The magnesium and ether, reflux a little bit. You make your Grignard reagent, it's the nucleophile, can quench it with a ketone or an aldehyde, and that's going to give you either this would be a tertiary or a secondary alcohol. So those disconnections are easy to make with ketones or aldehydes. And depending upon what the R group is, we can, okay, let's try an example here. So let's pretend that we've got and let's pretend that we've got or let's pretend that we have so okay, so this is a tertiary alcohol, this is a secondary alcohol, secondary alcohol. Let's do another tertiary alcohol here. So if we're gonna do some disconnections here. And I'll color them all different. Call this one A, call this one B, call this one C, call this one D. Yellow. Both of these are the same, so we'll color them rainbow. Okay, so now when it comes to this, so in each case, what we're going to be using is RMGX plus a carbonyl of some type. Now, in some cases, the really it doesn't matter. In some cases, it's critical as to which is the best line to do. So let's do one which is the disconnection is hopefully more obvious than, or is critical, I suppose is what we'd say. So in A, which line would be the one that you would want to break with doing this type of disconnection here? The orange line, the pink line, or the green line?
Would be green or pink.
Okay, so if we do green or pink, so let's see here. Let's do so this is going to be our ketone. And let's number this. 1, 2, 3, 4, 5. 1, 2, oops, nope. 1, 2, 3, 4, 5. So this would be our starting material, and we would throw in magnesium and, in fact, this reaction isn't called a Grignard reagent reaction because the electrophile is actually attached to the same, is it within the molecule. We could have some problems doing this. This is, so, yeah, because it's basically you're doing an internal reaction on itself, if it works. Probably the best disconnection here is going to be the orange one. Because we would have cyclohexanone and our I ran out of space, that's why I sort of drew it down. 1, 2, 3. This has got an extra carbon on it. Anyway, this is probably the better disconnection because this molecule itself is, there's some symmetry to it, so that's helpful. But you don't have to worry about an internal reaction which is taking place. I have to look up the name. I think this is a I'm spelling the last name wrong. That's why I'm hesitant to write it. It's not quite a Grignard reaction. It's so in this one I would definitely disconnect at the orange line for sure. Now with molecule B, which line does it matter which one's there, which one you break or which one you don't break? In this case here, the only things that you need to worry about. So if you're breaking the red line, if you do this disconnection here, you would have these two reagents as your two reagents. Methyl magnesium bromide, this is a common reagent, and 1, 2, 3 butanal. 1, 2, 3, 4 butanal. If you break at the blue line, I guess I'll have to move down a bit. It's the two components are going to be as follows. MGBR. The only thing I worry about is this really, you could get away with either one. It's not, this one might be a bit harder to manipulate. I don't know. I can't remember if it's a gas or not. Formaldehyde forms dimers and stuff like that. I don't know if this thing is a gas or not. I have to think about it. But it would all come down to just being a practical thing. Is like, what am I working with? Am I working with a liquid, or am I working with a gas or whatever? So most of these other disconnections aren't that critical. So you could get away with the light blue or the gray line. Either one would work. And then the far case over here, if you disconnect at the yellow line, you're working with acetone plus and that's perfectly acceptable. So this disconnection, Grignard reaction is a very, very, very reliable reaction to use. And it gives you lots of potential ways to, it's only in a couple, that gives you lots of options. That's the thing which makes it so wonderful. Okay, so if you want to make a carbon-carbon disconnection beside a beside a heteroatom like we did here, you can use the exact same sort of reagents, Grignards or alkyl lithiums, plus our friend the epoxide. So it's going to attack on the least substituted carbon, and you're going to open it up. So that's a really helpful reaction. Now, so that's if you've got an alcohol there. If you've got a carbonyl, so this actual step here is a functional group interconversion if you wanted to, oxidation or reduction. But there's a whole group of chemistry involved here where you put a negative charge beside a carbonyl and you use an electrophilic source of carbon. So because these are interfunctional group interconversions, it all depends upon your R group. Is it something which could be a good electrophile, or is it something which could be a good nucleophile? So it provides some flexibility. What some of you, let's go to the next screen here. So for everybody who took Organic 3, we would have seen enolate chemistry a lot. So let's just make this an aromatic ring for the sake of argument. So there's something interesting about these protons that are next to a carbonyl, that they can be removed with a base. And we could get into the base a little bit. And they would generate, so if you've got your base, this comes, grabs that proton, these electrons go there, those electrons go there. You generate a species that looks like this. And this is an enolate. We would have seen enols when we're doing tautomerization and that type of thing. But an enolate is has a nucleophilic carbon here. So in the presence of electrophiles, like say, these electrons can come down, and then these ones will attack, and you will form your corresponding product. So this is the alpha carbon here, alpha. And so it's basically making a bond, it's actually making a bond between the alpha carbon and the beta carbon. And so, yeah, this type of reaction with the enolate, this is basically, it works under SN2 type conditions. So electrophiles that are good with for SN2 reactions work quite well with these types of enolates. So allyl bromide, yeah, this reaction should be pretty high yielding. Now, what we did in class last year, it's actually interesting. We're not going to go into all the details right this second, but for people who were in class last year, there's actually two possible enolates you can make from this. One would be this one, and one would be, oops. Do we remember what the names were for each one of these for the people who were in Organic 3 last year? So we could actually control which one we made. Do we make this one? This was the kinetic enolate. This one was a thermodynamic. And typically enolates are, if you're using, if it's bonded to like a lithium atom, these are basically stable at minus 78 degrees. So you can generate like these enolates at minus 78, throw in your electrophile, and they can work. But there was specific conditions to do this reaction A, and there was specific conditions to this reaction to get B. And it's really versatile, because you can, if you've got a ketone, you can either have this as your nucleophilic carbon or this is your nucleophilic carbon, just based upon doing the reaction conditions and the reagents you use. So there's a whole, as we did a good portion of Organic 3 just based upon this enolate chemistry. So I'm not joking when I say you could have a course on this stuff, because you literally can. So there's all sorts of fun things with enolate chemistry here. And we'll see a bit of this when we're doing some of the syntheses. So, but the other neat thing, which is possible, is that, remember, if you've got this, you can reduce it to an alcohol, which gives the same sort of structure. Or if you oxidize your alcohol, it'll take you to the carbonyl. So what we're using here is a nucleophile. So there's multiple ways to make things that are very similar by just reversing the polarity of the carbon. Is it an electrophilic carbon or is it a nucleophilic carbon? So hopefully I can dig up some nice examples of that. Okay, let's think. Usually I stop at after an hour, but I seem to have burned right through that. Does anyone want a quick break?
Yes.
Super. Okay, let's come back at 1 o'clock. And we'll talk about the next one, which is the organocuprates. And I'll put this on pause. Someone remind me to re-record. Right, okay, sorry. Is everyone back?
Yep.
Okay, so the next little, actually it's kind of funny because we can do a lot of these same things using very similar sort of disconnection. So the next one here, if you need it, this is, again, we're making a carbon-carbon bond, and making carbon-carbon bonds are the super important, obviously, in organic chemistry. But if your R group is on the third carbon, so the beta carbon, we discussed this yesterday with regard to heteroatoms, like Michael addition. But today we'll just do something similar with regard to what we call organocuprates. So, and it's the same sort of thing. We would use an alpha beta unsaturated carbonyl. Typically it would be a ketone or an ester. And we would react it with an organocuprate. Now I'm going to change this. I'm going to go to the this one here. So organocuprates, you can make them from using two equivalents of some alkyl lithium and just react it with, it's technically copper-1. So the most common version of this is probably copper iodide. And you end up with this as your reagent, and there's lithium iodide as one of the byproducts of this reaction. And this is usually carried out in THF or sometimes in ether. The chemistry of organocuprates is fascinating. We could do there's what we call lower order organocuprates and higher order organocuprates. But one of the things which is interesting is there's two alkyl groups attached to it, but typically only one is donated. So if you are, but these alkyl lithiums, you can design or make these yourself. So if you can have a special molecule that is like, you can make these yourself. So an example of something that I did, when I was in grad school, I made an organocuprate which looked something like this. I can't remember. I can't remember. So I had some sort of silyl protecting group, and this was chiral, and I wanted to do a 1,4 addition on something. So because this thing was it took some work to make this chiral alcohol. I didn't want to use two equivalents to transfer one. So people have developed organocuprates where you've got one ligand, which is the one which is being transferred, and another ligand, which is what they call a dummy ligand, which I'll just call it R star. And this one is never transferred, excuse me, which is kind of neat. So there's a whole bunch of chemistry around organocuprates, which is quite fascinating. But the one thing which it's really useful for is that if you've got I will call this, we'll make a ketone here. It's typically done on ketones, but it could be done on esters as well. But organocuprates, they add on the beta carbon. So if you had R, this guy would go there, this would go there, that would go there. And so it's basically it's a conjugate addition, just like the Michael. And so you've got your R group is now attached to that carbon. And what do we have? I'll call this R star here. What do we have here?
An enolate.
Right, we've got an enolate. So we've got an enolate. And the wonderful, now you could actually quench this reaction with some other electrophile. So we'll call this RI. Running out of symbols here. R primed, I guess. So and this would be an SN2 type reaction. And so we could have this go, let's do this. Let's make this just very colorful today. And in effect, you would have R star, R primed. So in one transformation, you have made a bond here and you've made a bond here. So that's really it's really quite awesome. So sometimes this type of strategy is used where you're actually doing two steps in one, because the first step, you're actually making the product of the first step, which is the bond you want to make, perfect, but you're generating an enolate, and it can then react in the second step where you're quenching something. And which makes this even more wonderful, is that if somehow this double bond is, so what people have done to make these sort of connections, like to chiral, is I've used things like chiral catalysts for the some sort of chiral Lewis acid to complex to the carbonyl at the start, so the cuprate can only attack from one side. There's all sorts of fun stuff which is going on. So, but when it comes down to it, if you think back to if you have a system like this, I'll just draw a squiggly line for that. Put an R here. And I'll put an R here. There's a whole series of potential disconnections here. You can disconnect here, and that could be an organocuprate. You could disconnect here or here, and these would be, you'd start with an enolate and have, so this would be, sorry, this is an organocuprate with a nucleophilic R. You could use an enolate and have an electrophilic R or R primed. So there's a whole bunch of different things that you can do next to a carbonyl, and it all depends upon what those carbons happen to be. So, or it can be a combination of two, organocuprate and the enolate. So it's really quite awesome chemistry with regard to that. So we'll just keep that in mind when it comes to things in the future. The other thing which organocuprates do as well, which isn't talked about a whole lot in textbooks. So the acetate group, this is a good leaving group. But what organocuprates can do for here, it's called an SN2 primed reaction. And so the R group would attack here, and you would displace the acetate, and you'd lose your acetate because it's a decent leaving group. And the neat part about this is that you keep your double, like if there was a double bond, you keep it, and you can do further chemistry with that. And the other thing which is really interesting about this is that organocuprates. So I should. So organocuprates can do this SN2 prime type reaction on allylic double bonds. They and there's some stereochemistry just like in an SN2 reaction, and I think we'll see this a bit later on in the course, but it's something to look forward to. So organocopper is a rather wonderful reaction, and what I think for some of the classes in Organic 2, we would have done this reaction, R star. So organocuprates can react with acid chlorides, but they don't react with ketones. So this is a way of making ketones using organocopper as well. So that's just a, it's actually not what I was planning on talking about, but I got sidetracked on how wonderful organocopper is. So anyway, that's just something to keep in mind there. Alrighty. So, oh, here we go. So the great thing is that carbonyls and alcohols can be interconverted through reductions or oxidations. And there's lots of reagents to do this. So this is a totally reliable reaction. And so we can always disconnect beside a carbonyl itself and have our, the carbonyl being the electrophile and R being the nucleophile. So acid chlorides in organocuprates, that works, but you can also use other fun reagents like Weinreb-Zamide. So now, Weinreb-Zamide comes from essentially the acid chloride, which I've done here. So it's an amine which has got an oxygen on it. So this reaction is totally reliable, this one. But if you react Weinreb-Zamide with an alkyl lithium or a Grignard reagent, the fun thing is that you make a ketone. It doesn't get over, the Grignard doesn't add twice. So if you had, say, or if you had an acid chloride and you used a Grignard reagent, R primed is going to come in and attack. Electrons are going to move up. Electrons are going to move down. Chlorine is going to leave. You're going to have R star. And this ketone, another equivalent of the Grignard reagent, is going to come in and attack, and the electrons are going to move up. And you're going to end up with an alcohol, a tertiary alcohol. But with Weinreb-Zamide, it actually stops at the ketone, which is nice. Yeah, and esters are very similar in the sense that you're going to generate a ketone, and then the second reagent is going to add twice. So you're going to have two R groups that are identical. So and the reason why Weinreb's amide works, which is really, it's a fascinating little thing too. Let's do that. So let's pretend that you've got methyl lithium. So this methyl group's going to come in and attack. The electrons are going to move up. So this should be a tetrahedron that I'm drawing. And I'm going to just, the lithium is going to end up on the oxygen. The fun thing is that it forms this little complex where this is a, what is this? A 1, 2, 3, 4, 5-membered ring. And that is, so it basically, it's quite stable. And it sits in this, so this is effectively oxygen with a negative charge here. It sits in this until you do the workup, when you add H2O. And then it falls apart. H+. So let's protonate this. R OH N M E. And we've got, if we look at this here, oxygen, carbon, nitrogen. This is basically an aminal. And they're not stable under acidic conditions because we'll just protonate the nitrogen and then we'll boot everything out. So, so let's do that. So this is a methyl at the start. Boot that out. And then you've got your ROME. The proton here will get removed by the solvent, and then that will just get transformed into your ketone. So it's this really, really ingenious little forming this 5-membered ring that that works. And this works so you can reduce with Weinreb's amide. You can reduce something with lithium aluminum hydride. You'll make an aldehyde. So it's just a wonderful little. It's a wonderful little addition to wonderful little tool, I guess. So, right. So the second option for carbonyls, this one we haven't seen before, and it's really strange in the sense that it's completely the reverse. It's having the carbonyl with the negative charge and your R with the positive charge. We don't see this as often, but there's a reason why I included the thioacetals earlier, or dithiones. That's because these protons are relatively acidic, pKa of 31. That means that you can remove it with something like N-butyllithium. And so it's got a negative charge. And then this will just basically do an SN2 type reaction. And then you could remove the other proton and do a similar sort of SN2 reaction. And before you know it, you got butane and ethyl. And then the acetal, or the thioacetal, can then just be deprotected. They use mercury dichloride. That's a common deprotecting group for this. And sometimes using mercury isn't particularly the funnest thing in the world. So, so here's an example using mercury to make the ketone. But what we might have done in organic 2 is the uranium nickel reduction, and that just chops that off entirely to make 2 protons. So this is a way of converting, say, a carbonyl compound into another carbonyl compound, or actually reducing it entirely. So there's some things to do there. Oops. That's supposed to be an oxygen. So there's a way of using dithiones to make this type of structure, if you want to have some fun doing that sometime in the future. Okay, so let's think here. Okay, so it looks like next class, what we'll do is a little, for some of you, this will be a review from Organic 3. For some of you, it'll be completely new. And that is what we talked about a little bit before, enolates. So this is a negative charge beside a carbonyl. And typically, these are either ketones, esters, or amides. Aldehydes, not so much, and we'll see why in a little while. There are like enolates, the stable enolates, where it's actually oxygen with a negative charge or oxygen bonded to lithium. We would call these lithium enolates. Or the other one is if you've got a silyl group. So TMS, remember, is oxygen, silicon, and then 3 methyl groups. So both of these are enolate or enolate equivalents. Both of them are relatively stable. One's at -78 though, and the other one is at room temperature. And we can use these to react with electrophiles. And they both react with different types of electrophiles, so they're complementary. But this is what we'll do. This is where we'll start off next class. And the aldol reaction is when you use an aldehyde as the other coupling partner. And so that's why typically aldehydes aren't used up here. It's these other versions. But yeah, we'll do the aldol reaction on Tuesday, I guess. And then the reactions that follow are all derivatives of that classic reaction. So it's all about using enolate chemistry to make a disconnection on the alpha carbon. I blabbered quite a bit. Any questions at all? Okay, so I'll try to devise some really fun pre-class questions using what we went over this last class. And then we'll talk about aldol reactions on Tuesday. All right. Until then, I'll try to get back the first lab thing. I'll start marking those tomorrow, I think. But until then, if you've got any questions, don't be shy, and I'll see everybody next week.
Bye, Dr. Young.
All right, see you.
Thank you, Dr. Yan.
Oops.